Okay, so we're going to go through some whiteboard problems now. So these examples are from your textbook. So for each situation below, show the energy transfers and transformations on an energy bar chart. Is the system energy conserved? Is mechanical energy conserved? And think carefully about the system in each case. So we've got three examples, and the first one is a speeding car skids to a halt. The next one is a rope lifts a box at constant speed. And the last one is the box lifted in the previous example falls at a steady speed as the rope spins a generator and causes a light bulb to glow. And in this case, we'll ignore air resistance. So you might want to think about that for a minute. Just hit pause on the video and think about your answers to those things. So about the questions, that are up in the top, and then think about your answers before going on. So here's an example of the energy bar chart for the speeding car skids to a halt. So you can see before K initial, the speeding car has a velocity. It doesn't have any potential energy. It's on the road, so we know that all of its energy is kinetic. And then final, we know that it's stopped, so it has no kinetic, still has no potential, and all of its energy went into thermal energy, and that's lost. That's a non-conservative energy there that the friction, right, is the result of that, and so that goes into delta E thermal. So if we think about the next one is a rope lifts a box at constant speed. So think about that before you go on. So here's a rope lifts a box at constant speed. So thinking about this, we know that we have kinetic energy because the box is moving, so it has 1/2 mv squared, it has kinetic energy. And it also has the tension from the rope, which is an external energy, an external work term that's lifting the box. And so those are our two values there. It has no potential energy at the initial position, which we're calling 0. And then final, it has the same kinetic energy because the speed hasn't changed, but now it has potential energy. So you can see it has U final, and so that's its potential energy. It would be mgh for however high the box has been lifted. And there's no E thermal. So this is all of the energy is conserved in this example. And then last is the box lifted in the previous example falls at a steady speed as the rope spins a generator. So if we look at that one, we can see here we have the box is being lifted, so we have kinetic. We have potential energy. The box is being is moving downward at a constant velocity, so it has a potential energy. It's falling. That's the blue bar. It has work external, but it's negative here because the work is going in the negative x direction. So it's going, the box is moving down, and so that's against the force due to tension. And so finally, you can see here we have our kinetic energy, and then we have no thermal, and we have no potential energy, and so all of that energy goes into the energy of the light bulb being lit by the generator. So that's not conserved as well. We're going to skip here. Let's see. We missed a few problems here, so I'm going to go back. So here, I wanted to talk about this problem. So this problem is a think, pair, share, and let me pull this up. So I have a think, pair, share, and Robert pushes the box to the left at constant speed, and in doing so, Robert does what kind of work on the box? Positive, negative, 0, or imaginary? And so the way to think about this is that the box is moving to the left, and Robert is exerting a force in the same direction that the object is moving. So the force and the motion are in the same direction. So we should have a positive force or a positive work on the box. So right at the bottom here we can say force is in the direction of displacement, so therefore we have a positive work. Here's another think, pair, share. So a light plastic cart and a heavy steel cart are both pushed with the same force for a distance of 1 meter starting from rest. And after the force is removed, the kinetic energy of the light plastic cart is blank that of the heavy steel cart. So how do we think about this? Well, we know that the work is, so W work is equal to delta K. And so we want to see if the work is different between the two carts. And so how do we determine work? That is, work is defined as the force times the displacement over which the object moves. So here we have the same force, both are pushed with the same force, and our distance is 1 meter, so they're both going to be moved the same meter, so the same displacement. So that's going to be force times 1 meter for both. So that tells me that the kinetic energy, will be the same for both. So I would expect this to be B equal to. And yes, that's true. So same force, same distance is the same work done. And work is defined as change in kinetic energy, so we know that it's the same. If this question had asked about velocity, is the velocity of one cart larger or smaller, then they would be different. So just something to think about, the difference or the similarities between our work kinetic energy theorem and the impulse momentum theorem. So we learned about the impulse momentum theorem in chapter 9, and we can see the impulse is the change in momentum, and that's given by the area under the force time graph on our left. So if we can take the force, the average force times the time over which our force acts, we can find the change in momentum. Whereas for work, we want to find the work kinetic energy theorem. Delta K is the same as, is equal to, our change in kinetic energy is the same as the work, and we can find that by finding the area under our force displacement graph. So we can just take the area under this, say, triangle, and we'll be able to find our work or our change in kinetic energy. So let's look at a problem here. We have a group whiteboard problem. We have a rope, and the rope is at 45 degrees to a suitcase which is being pulled through the airport. The tension in the rope is 20 newtons, and we want to know how much work does the tension do if the suitcase is pulled 100 meters. So one thing to think about this problem is we know that we only have work in the direction of motion. So we can see here that our tension is in both an x and y direction, but our motion is only in the x direction. So we're only going to want to consider the component of the tension that's in the direction of motion. So that looking at this picture, we would want to have the x component of tension. So that would be T cosine 45 degrees. So let's look and see if we can do this problem. I move this over. So I know in this example, close this, that I've got my tension looks like this. So this is my T. This is my T cosine theta, or cosine 45. This is my theta. So I know my work is going to be F in the x direction times delta x. And I know my object has moved from, say, this location to this location, and this x initial is 0. I'm setting that equal to 0, and our x final is going to be 100 meters. So here I want fx, and so my fx is going to be equal to T cosine of 45. And then my delta x is going to be times 100 meters. So my work is going to equal 1,400 joules when I plug in those numbers for tension here. So we have a work of 1,400 joules. And this is an example from Knight. You can check on that in the book. And we'll do another whiteboard problem. So in this example, we have a rocket that's launched straight up. It's a 150,000 kilogram rocket, and the rocket motor generates a thrust of 4 times 10 to the 6th newtons. So what's the rocket's speed at a height of 500 meters? And we'll ignore air resistance and any slight mass loss. And you can see here we already have a free body diagram. That's very convenient. And so the free body diagram, we can see that the force of thrust is bigger than the force of gravity, which we would expect because the rocket is going straight up. And so we need a upward force in order for the rocket to overcome gravity. And the other thing to notice here is that my delta K, right, is equal to the net work. And so it's asking me about the rocket speed. And so therefore I know delta K is going to give me that information because delta K is 1/2 mv squared. So in this problem, I'm first going to solve for work, and then I'm going to plug that into my change in kinetic energy to find my final velocity. So here, what I want to know is I want to know the work. If I can, the work in this case is equal to Fy times delta y. And my Fy is going to be my force of thrust minus my Fg. So in this example, then I can figure out my work is going to be work is equal to F thrust minus Fg times delta y. So, so now I can say, okay, I'm going to set that equal to delta k. So delta k is equal to W. And my delta k is 1/2 mv final squared minus 1/2 mv initial squared. Remember, delta is always the final minus initial. So if you're ever wondering, you always know it's the what you end with minus what you started with. It's equal to W. So here we know we started from rest, so this term goes to 0. And so I'm just left with 1/2 mv final squared is equal to F thrust minus Fg. Oops. Oops. Did I get back here? So minus Fg, and this is going to be delta y. So so I'm going to multiply through by 2 and divide by m, and I get V final is equal to F thrust minus Fg delta y times 2 over m square root. And when I plug the numbers in, I get my V final is going to equal 130 meters per second. And so again, this is an example from the book, so feel free to take a look and make sure that you understand how that problem works. Okay.